Hi, hello. Welcome back. This is another lecture on the foundations of machine learning. So, in the previous lecture, I think we went over the concept of vectors, right? And today we're gonna talk more about matrices in terms of like what they do, what's the point. So, I'm Professor Wu. Let's get started. All right. So previously, remember that we had an example where we were gathering data about Northeastern University students. So we were collecting a single sample. So we asked one person their age, their height, SAT score, and once we finish asking all these questions, we collect the data into a column of numbers, which we call vectors. Right. So this column of vector we represent as x1 as the first person. So of course, in actual real life, you don't just ask one person. When you take a poll, you are asking a lot of people. So you result in having many, many vectors. You have x1, x2, x3, x4, so on and so forth. And today we can have hundreds of thousands, millions, billions of data samples. And each sample is a single vector. So in order for us to put all these data together, what we do is we convert each column into a single row. So we convert x1 into x1 transpose. So now it's a single row. And then we kind of stack them together. We start stacking. So you can see now you have rows and rows of samples. Therefore, however number of samples n that you collected, how many people you asked, like the question is how many rows we have. And then how many questions you have is how many columns you have. And this together is how we normally represent the whole data set, or we call it the tabular data set. In this setting, we also call it the matrix. The matrix. So a vector is a single column. A matrix is a vector of vectors, essentially, right? And symbolically, we represent matrices and vectors differently. Matrix, we use capital letters, while vectors, we use lowercase. So when you see lowercase, uppercase, you can immediately realize, we are talking about vectors, we're talking about matrices. Okay? So you can imagine most of the time what we do is we take the each sample we collected, convert them horizontally and kind of stack them. And that's what give us the entire data set. Okay? So in the previous class, like we talked about how vectors are the units, the smallest unit we deal with in like the big four, like machine learning, data science, robotics, right? So vectors are very important, but collection of vectors which form the matrix, right, is also very important because we're ultimately we want to manipulate multiple vectors simultaneously. And matrices allow us to perform these kind of manipulations. So previously we learned how to manipulate vectors. In this class, we're going to learn how to manipulate matrices. Just basic operations like what I told you previously, addition, subtraction, multiplication. I don't think we're going to do division in this class, but just the very basic three: addition, minus, subtraction, and multiplication. So that's the point. Okay, this is how matrices come about. And with matrices, it's two dimension, right? It has all the rows, all the columns. So the way we denote them is we're saying that for this matrix, we have 100 rows and 3 columns. And when you see this notation, it's basically telling you the size of the matrix. Okay. All right. So let's get going. Let's start with various matrix shapes. Well, if you have a matrix where the number of rows and the number of columns are the same, we call these square matrix. And it makes sense because, well, it looks like a square. So this is a square matrix. However, not all matrices are square. Sometimes you'll have much wider ones. The ones that are wide, traditionally in engineering, we call them fat matrices. And the ones that are long, like this, they're called tall matrices. So these are just some kind of nomenclature. So when we talk about square matrix, it's exactly the same dimension for the number of rows and the number of columns. And just like vectors, remember in vectors, we can transpose them, right? So with transpose, if you add a transpose symbol, you basically convert all the columns into rows, like such. So that was for vectors we learned last time. Matrices is exactly the same. When you perform a transpose, you convert all the columns into rows. So 1, 3 becomes 1, 3, right? 2, 2 becomes 2, 2. 7, 0 becomes 7, 0. So you just essentially convert all the columns into rows. And that is a transpose itself, right? And of course, if you were to do a transpose again, all the columns will turn into rows again, right? So you will get the original matrix back. So if you have two transposes, first, second, you just get the matrix back. Now let's try this yourself. Here we have four matrices, and you can essentially just see if you can get the solution after you perform transpose on each and every one of them, like such. All right, what is this? Okay, pause the video. You can give this a try. And yeah, the solution is in the next slide, essentially. Okay, so pause the video. Make sure you do it. All right, so now that we've done the basic transpose operation, let's do the most basic addition and subtraction. Well, addition and subtraction is just like vectors. Nothing different. If you have two matrices A and B, and you're trying to add them together, where you have A plus B, well, you just take each element, 1, 5, add them together. And then you take the next element, 3, 7, right? As a result, you essentially just take every single element, add them together, and it results in another matrix. So the addition of these two matrices gives you another matrix. And it shouldn't be a surprise that subtraction is the exact same idea. If you have two things subtract each other, it would be 1 instead of plus 5 is going to be 1 minus 5, right? And then 3 minus 7, and then you have what, 2 minus 6 right here, and then 4 minus 8. So addition and subtraction, very, very simple, very similar to whatever we were doing with vectors. The next one, if we have multiplication, so let's say we have X matrix and we multiply by number, 2x in this particular case. So what you do is you just take 2 and you multiply by every number in here. So you have 2 multiplied by 1, 2 multiplied by 0. So that's when you see this notation where you have 2, a constant value, multiplied by a matrix. What that just means is you have a number multiplied by every element in the matrix. Similar for addition, when you have x plus some number, all that means is you take 2 and just add to every single number into x. So that's just a matter of notation. You need to recognize and know what it means. Okay? And now we're ready to move into multiplication. And the simplest multiplication is the Hadamard product, which if you remember from vectors, a Hadamard product is simply a multiplication of elements. So you take the first one, multiply by the first one, right? Second one, multiply by second one. Third one, multiply by third one. Fourth one, multiply by fourth one. So the idea of the Hadamard product symbolically is the same as the one we use for vectors. But the idea is exactly the same. You take every element and just multiply them together. Okay. Now with Hadamard product, it's very important that the two matrices has to have the same dimension. So this is 3 by 2, 3 by 2. Both has to be 3 by 2. Both has to be 2 by 2. If they don't have the same dimension, the operation doesn't even make sense. Okay, so that's Hadamard product. And now we're ready to move on to the most important operation. This is the most important operation for linear algebra, and this is called the matrix dot product. So we previously learned vector dot product. Now we are learning matrix dot product. This is traditionally you can write the dot, right? Symbolically, you can say just x dot z, right? But because this is so important, this symbol is normally just ignored, neglected. So what we do is instead of writing x dot z, this is the default operation. We just have x times z. So when you see two matrices next to each other, like x and z, you automatically assume that it's a dot product. Right? That's the standard because this is the most used operation in linear algebra. And the way we perform this operation is that we follow what we did with the dot product as vectors. So we have two matrices, x and z, right? So how do we go about performing the dot product? Well, we look at z, the first column, as a vector, and the first row of x, and then we perform dot product here, which, if you remember from last class, it's a vector and a vector. When you perform a dot product, it gives you a 1. And then you still keep the same 1, but you move on to the second column. So now you take this one and then this one, and you perform dot product, which give us this value. And then you keep going again. You take the first column, now this time the second row. You take dot product, and you get this. Lastly, you take the last column and the last row, you perform dot product. So basically, you are going through every single column, and multiply by every single row. And then every combination of that is the result of your final dot product. So a dot product is a combination of bunch of dividing the matrix into multiple columns, multiple rows, and then find the dot product between these columns and rows in every combination. Okay, so that's the idea of a dot product. So matrix dot product takes a bit of practice. So at this point, like compute a product, I want you to see if you can multiply this. And then try this one. This one is 3, and then this one as well. So you want to think about the operation and see if you're able to like absorb how you perform this like matrix dot product in general. Okay, pause the video to do this. The solution is right here. So that's the solution for this, and the solution for this is here. Okay, so you can pause and get the solution by looking at this. Okay, so now what if you have a matrix multiplied by a vector? Well, notice how over here we have a matrix and we are multiplying by vectors, so xw. Well, the way you do this is you just treat this vector as a matrix of one column. So this is only one column. This means you take this, multiply by this, and then you take this again and multiply by this. So that's basically how you will perform this. Right. Similarly here, instead of multiplying on the right, we multiply by the left. You also treat this right here as a single row, right? Therefore, you take this and multiply by this, and then you take this and multiply by this. Okay. Next, we have the diagonal and trace of a matrix. Well, let's say we have a matrix. The diagonal operation, diagonal. If you're trying to find the diagonal of x, all you do is you take the diagonal elements and convert them into vector, right? 149. Notice how this is 149 as well. All right, here's another example. You're trying to find the diagonal of z, which you just look at the diagonal elements, 4 and 1. Now the diagonal element's always this way. Okay, it's never this way. So this way. Okay, so now if you have the diagonal elements, you can learn this operation called the trace operation. The trace basically takes the result of your diagonal elements and add everything up. So 4 plus 1 will give us 5. So if we find the trace of z, we basically find the diagonal and then add all the numbers up here. Similarly here, trace of x, right? We take all the diagonals and then add all the numbers up. So that's what a diagonal and a trace of matrix is. All right. I think this is one of the last one. Matrix inner product. Well, remember you learned the inner product symbol. The matrix inner product is basically when you take x, right, the first one, transpose times y, and then you find a trace of the whole thing. It turns out that if you place the transpose here or here, it doesn't matter. They're mathematically equivalent. So for this particular example, if you want to find the inner product between x and y, we can use this definition. And basically, we take the first matrix and the second matrix, x and y. And what we do is we just find the transpose of this. So transpose becomes this. We multiply them together. And then we sum up the diagonal, which is equal to 5. So when we talk about trace operation, it's a particular operation, and later on you'll see why we'll use it. It's mostly based on this equation. So you need to understand what a trace is, as well as what an inner product is. Now, in NumPy, inner, when you do the inner product, you only perform this part and it doesn't perform the trace. So when you do NumPy, you got to remember to add the trace operation. Now, okay, now that we found the trace of x, the inner product between x and y, why don't you find the inner product between y and x so you can flip them? Okay. All right, pause the video, give this a try. The solution is right here. You can look at it. All right, so now we're ready to put everything together. All right, so pause the video now. We're going to do all these operations so you can get a handle on, like, kind of have these operations absorbed in your mind. Okay? Pause the video to do this, and the solutions are here, as well as here, as well as here. Okay, so we're going to move on. All right, part 2. So now that we know the basic operations of matrices, let's also look at some properties. The first property we have is called the associative property. That means if we have 3 matrices, A, B, C, you can multiply A, B together first, then multiply by C. Alternatively, you can multiply B, C together first, then multiply by A, right? So this move on if it's a constant value or a vector. So this is a vector or a number. You can multiply them together first, or you can multiply B and C together first. So this right here is called associative property. And when you have the chance, look through the examples and you will see that this property holds. The next one is called distributive property of matrix. So basically, you kind of already know this from algebra. If you have a number, multiply this and this, right? And it turns out that this property holds if you have A times B together plus A times C, like such, right? They're equivalent. And this is equivalent on the other side as well. So A goes here, A goes here. So A can be distributed. Again, I wrote like a bunch of examples. You can look at it and confirm that this property indeed holds. The matrix transpose. Okay, so if you have addition of 2 matrices and you're trying to take the transpose after they add up together, this is equivalent to taking the transpose of the first one plus the transpose of the second one. Okay? So this is the transpose property for summation. Transpose property for multiplication. If you have two things multiplied together, AB, and you want to take the transpose, this is equivalent to flipping the two matrices and putting a transpose on each. Okay? So this right here is the transpose property. Now, unfortunately for matrix multiplication is not commutative, which means that if you have two matrices, X and Y, it's not equivalent to Y times X. So this you need to understand. Like for a matrix, there's some similarities to algebra, but there are some things that you need to take note. And this is something that you need to take note that they're not the same, right? Over here, I wrote an example. If you have X and Y, notice how XY give you this, YX give you a different matrix. Therefore, XY does not equal to YX. All right. So we went through some of these properties. Let's practice. Let's practice what we just learned. Right. It takes a little bit of time to absorb these information. So use the matrix properties and show that these are the same and these are the same. Okay. Take a second, pause the video, and go over these. Okay. Here's the solution. Kind of shows you how why they're the same. Here's the solution for the part 2. All right, so we're ready to move on to part 3. And the part 3 is, well, I told you that matrix and vectors are really, really useful. And they're useful as in terms of data. But they're actually also very useful in terms of representation of equations and large equations. Very often in machine learning, data science, we have a lot of data which we can use matrix to represent. But then we have gigantic equations, which we also use matrix and vectors to represent. And what we have very often is what we call a system of equations. So let's say we have a equation, right? So equation of two variable, x1 and x2. So this function takes in two variables, right? X1 and x2. And if you plug x1, x2 in, it outputs some value. So this is what a function does. You put something in, you get something out. Now, with this function, notice how we can split this function into a vector, 2, 3, and another vector, x1, x2. And we are going to call this vector just A transpose, this vector X. So now what I'm saying is we can represent this function this way, which is the way that many of us are more familiar with. But from now on, realize that we can represent functions equivalently using vector-vector multiplication, right? So vector-vector multiplication. Now you might be wondering why we would want to do that. I mean, this is pretty clear, right? Why would we want to write it this way instead of this way? And the reason is because this is a very simple equation. But you can imagine if we have an equation with tens of thousands, maybe even millions of variables, x1, x2, like really, really complicated equations with thousands of variables, then you end up having to write something really, really large, right? So would you rather write like x1, x2, x3, all the way to x thousand, or would you rather write this, right? And this is just a much more compact way to represent unlimited amount of variables. And since in machine learning and data science, we end up having a lot of variables. It's just so much easier and more compact to represent things this way, right? And then we know that A is simply a bunch of numbers, 2, 3, 4, 1, right? And then X is x1 to x thousand. So this is this is just a superior way to represent giant equations. And that is just one equation. Very often what we have is a system of equations. So over here, right, we have a function that takes two inputs and give us three outputs. Right? So uh, if we plug x1, x2 in here, notice how it outputs x or three numbers. So if we plug x1 as 1 and 0, right, it outputs three values. So this is what we call a system of equation, because it's no longer having some input with a single output. What we have now is multiple potential inputs and multiple potential outputs. And in those cases, then we also need to represent the equation. So notice how right here, this same equation could be represented this way. 1, 2, 0, 1, 3, 1. 1, 2, 0, 1, 3, 2, 3, 2. So if you take x1, x2 and multiply by it, then these and these are mathematically equivalent, implying that, well, this is a matrix, this is a vector. We can write a very complicated set of linear system of equations into something very compact and easy to manipulate. So, so now you kind of see that, yes, matrices are useful to represent data. They're also useful to essentially represent large equations, like very large equations. All right, so these are some operations that we've learned, like multiplication, addition, and of course, like with thousands and thousands of numbers, you don't want to be doing it by hand. Most of the time, instead, we calculate this addition multiplication using Python, almost like a calculator. So over here, you see, you can define a matrix A, right, like such. And you create the A, you can define a vector using this notation. You can define another matrix. And once you have these values, A, B, C, defined, you can now perform operations on them. So you have A dot B, right? So A dot B. So you just kind of multiply them together. Or A dot C, you're multiplying two matrices together. Now remember, A dot C can also write the add, right? That will also work. So this, like, you can look up the notation yourself. You just want to be aware that when you're actually working, you have these giant matrices. You don't want to be like calculating by hand. You should know how they're calculated, but like most of the time, you also want to know how to calculate them with computers. Okay. All right. So here it is. I want you to pause the video and practice converting these systems of equations into the matrix format. And then after you're done with that, do it backwards. Right over here is a matrix format of the equation, and you want to convert this back into a system of equations. Okay, pause the video. The solution is here as well as here. Okay, so once we're done with this, your very last exercise of the day that is essentially allows you to review the entire class. What you want to do is you want to answer these questions as well as this one. Okay, so pause the video now, and then essentially you can go over these questions, and they should reinforce a lot of the concept we learned in this class. Okay, as always, here's the solution for some of the questions, and here's some of the other solutions, and I think I have more here. Okay, so the solutions are provided, but you should definitely go over the exercise yourself. All right, so that's the end of today. Make sure you submit your in-class work, and make sure you submit all the code, screenshot, and you have about 30 minutes until you have time to submit this. All right, thank you very much. See ya.